Hello, in this video we'll cover the material from section 9b. This is our last section. This is really our last overall lesson. We mentioned a few of the initial ideas in class on Monday, but we're really going to hit all the important points and see every problem to its full extent. But this is a continuation. We're still talking about the ideas of functions. We still have the ideas of x, y, of independent, dependent variables, and we've already seen how important units still are here. Always on our graphs displays, we want to keep very accurate track of what we're measuring, including the units, and we've also started to see how units can help us solve these types of problems as well. So that's the direction we're going. Very quickly, just to remind you of our remaining schedule, on Monday, that's our last day of class. On Monday, we're going to do three things. We're going to do some review from section 9b. After the class is over, I will distribute test 3, so that'll actually come up on Tuesday, not on Monday's class, and test 3 will be a take-home. You will have that, work on it on your own, and turn it in on Monday, the 23rd. That's the same day as our final exam. So this Monday is our last day of class. You will get test 3 distributed and turn it in on Monday, 5/23, our final exam, our regular meeting time and place, just that we get 2 hours for our final. So the final Monday, the 23rd, and that'll go from 6:10 to 8:10 p.m. We normally meet 6:10 to 7:25, but again, we get full 2 hours for the final exam. So test 3 goes out after Monday's class, take home, you hand it in, and we'll discuss more of the details of the final on Monday. So that's the second thing. First thing, we'll review this. Second thing, we'll just discuss some of the extra details on the final. Remind you it's an open book, open note, give you some study advice, remind you of some of the situations that you might want to consider, but all that'll be Monday. And the very last thing on Monday, we are going to do Lab 4. It is going to be very quick. It's going to be very easy. So just several items that it's really, really important to make sure you attend Monday's class to get all these final details and make sure you're on track for the rest of the semester. For homework, this is our last homework. From section 9b, page 537, we've got these problems: 11ab, 13ab, 17, 21, 23, 29. And then for number 43, there's a whole bunch of directions right before number 43, but ignore the directions. Just read the problem in 43 and just answer the question. That's all I want. Okay, so linear modeling. That's what we're looking at here. We've already discussed functions and the idea of mathematical modeling, but now we're specifically looking at linear functions. What is linear? A function is linear when all of its points line up in a perfect straight line. That's the idea of a linear function. So if we read this problem, we're talking about how the depth of rain accumulating in a rain gauge as steady rain falls. The rain stops after 6 hours. We want to describe how the rain depth varied with the time during the storm. So just thinking about our basic setup, we're looking at the time during the storm, how long the storm has been going on, and we're measuring how much rain has accumulated during that storm. So those are our two variables. Time will be our independent variable, hence that would go on the x-axis, and the rain depth would be the dependent. The amount of rain that has fallen depends upon how much time has passed. So that's how they generated this model. And, they just already set this up for us. So if we're looking through, we can understand, okay, it just started to rain. We've got no depth. After 1 hour of rain, we've got 1 inch of rain that has fallen, and then we can keep going. They then reiterate the importance of the slope, that the idea of the slope of the line is discussing the rate of change between those two variables. That idea of slope, which gets all brought up on this second page here, once we flip, this idea of rate of change. We keep seeing the importance of that topic, and if we're looking for the rate of change, that we can find that rate of change with this idea. That we reminded, for a lot of people, remembering the algebra idea, the idea of slope of the line, but in order to find that slope, we do the change in the dependent variable, so that's the change in y over the change in the independent, so that will be the change in x. So let's see how they computed that. They're still thinking of that range situation, but now they're showing us several different models, and let's find the rate of change. See, that's one big thing. Since this is not an algebra class, we are reminded that the rate of change is the same thing as the slope, but in our wordage, when we are seeing a problem, we are going to be asked things like the rate of change. So if I give you this model and ask the rate of change, well, we're basically following this idea. So I'd have to find 2 points. So they're doing a couple things here. They're showing it in a few different ways. And one of their reasons for doing this is to show that in a linear model, if we are going to get this straight line, the rate of change must be constant throughout. So just jumping to this one, notice what they're showing here. The change in the dependent over the change in the independent. And no matter where we go, we're seeing that as a constant. That if I look over 1 hour of time, my rain depth has gone up another 1.5 inches. Well, I go up here, I look at another 1 hour of time has passed, the rain depth has once again gone up 1.5 inches. And that's what they're demonstrating here as well. Now, they're also trying to point out a little bit the steepness, to try and point out if your line is steeper here compared to here, the rate of change is greater. Here, the rate of change is only 1/2 inch per hour. Here, the rate of change is 2 inches per hour. That's a bigger number, hence we're getting a steeper slope. So that's a nice observation, but I'm not too worried about that. For right now, I just want to focus on how they got these values to show how we could use this basic idea to figure out the rate of change. So the idea, though, let's find 2 convenient points. See, that's the big thing. When we're doing rough sketches like this, and these are not exactly rough, the book did a very good job, but we don't have the full grid on like having graph paper. So if we just randomly pick a point, it's not always going to work out nicely. So we want to pick nice points. So looking at this first one, let me focus on this point for a moment. Notice this point very nicely lines up that the time is 2 hours has passed and that we have accumulated 1 inch of rain. If I go to this point, well, this point nicely lines up with 3 hours, but now I'd have to roughly ballpark what this is. So it is about 1.5 inches, but that's a rougher situation, so let's not choose that point. Let's choose this point instead. This point lines nicely up with 4 hours and with 2 inches of rain. So if I identify these 2 points, this would be 2,1, 2 hours for 1 inch of rain. This point would be 4,2, 4 hours for 2 inches of rain. So if I follow my blueprint here, my slope, my rate of change, and let's just note this is for part A, I would take the y value minus the y, so I do 2 minus 1, over the x minus the x, which is 4 minus 2. I get 1 over 2, but the units, technically the units are in each place here, but it's easy enough just to put them in the end. The units from the y was inches of rain, so I'll just put inches, per, and my time is measured in hours. So this 1/2 would have units inches per hour, or 1/2, which is the same thing as 0.5 inches per hour if we use our proper division notation. So that's what we're seeing right here. 1/2 inches per hour or 0.5, same thing. Similar with the next couple, and same thing. Let's pick good convenient points. So similar here, I'm trying to find good points. Well, if I go to 1, it doesn't line up nice. I go to 2, that one lines up pretty nice. If I go to x is 2, my time is 2, I'm seeing the y is 3. So that would be 2, 3. Keep going. This one doesn't quite line up nice. 4, still not quite lining up nice. But there we go. If I go to 4 hours, I see that lines up nicely with 6. So now if I do part B, that same rate of change, here's one thing I was mentioning in class, the importance of being consistent. Most people have a natural tendency to just try and do bigger number minus smaller number, but not too far into this, we're going to see the possibility that a slope could be negative. It doesn't have to be positive. Just to realize that in every example here, the amount of rain is increasing over time, hence this has this upward trajectory. But in a few minutes, we'll look at an example where we're looking at something that leaks, an object that leaks, so it will lose volume over time. It'll have a downward trajectory. So the plus or minus part of the slope of the rate of change would be the indicator that my rate of change is either growing or shrinking, decreasing. So that's why we need just to be consistent. We can't just do big minus small. It's easy to start that way and say, okay, I'll start with the 6 for the y minus the 3. But once I establish that, I use this y first, and then I follow with this one. So now I have to use this x first, followed by this one. That becomes 3 over 2, which is the same thing as 1.5. And we still have those same units, inches per hour. And we could see down here, that matches what we have. So you can do that same thing here if you like for a third example. But just to point out, if we already have the graph, and a little later on we'll realize what we're really doing here, it's not so much about using the graph, it's having two data values. If you have two data values, you can then figure out the rate of change. And if you have the rate of change, there will be questions that we could answer that follow from having that information. So let's keep moving along here. So a lot of nice work established. What is a linear model, first off? Getting into that deep concept, the idea of slope and rate of change, how we compute it, getting our units attached, and the real idea of what's actually happening here. So if we move along, and now we get to example 1. Let's actually make a linear model. So they give us this nice example. You're hiking a 3-mile trail, but you're increasing elevation. Okay, they should have given us a tiny bit of a better description before they jumped in here. The idea, we're going up into a mountain and we're doing a 3-mile walk, but as we walk, we're continuing to climb up and up the mountain. So at the beginning of the trail, we have an initial elevation of 8,000 feet. As we continue the walk, the trail gains elevation at a rate, there's that word, a rate of change of 650 feet per mile. So the elevation along the trail can be viewed as a function of the distance walked. So here it might be a little confusing because these are two distances. It's nice. For a lot of examples, we'll see how time works very nicely as the x variable, as the independent variable, but it's not the only possibility. So in this one, the literal distance that we walk, we do that independently, but then our elevation, that depends on how far we've already walked. So we're getting that independent-dependent relationship here. And even just thinking about the units here, once we saw this rate, this idea of 650 feet per mile, well, we're already setting up. The feet measures the elevation change. There's the y, there's the dependent. The mile, how far we've actually walked. That on the x-axis, that is the independent variable. So, if we have this information, I just want to ask a quick question here. So just thinking about this. We start at 8,000 feet, and as we walk, we increase that at 650 feet per mile. What is the elevation after walking 2 miles? How would we answer that question? What would we do? Well, the one thing to first point out, a way to answer this question would be to make the model. how did they make this model? They said, okay, hey, if we start at 8,000 feet, that means we haven't gone anywhere, we haven't walked anywhere. Starting at 8,000 feet, thinking of the XY setup that we've presented, where X represents the distance walked, and then Y is the elevation to go with it, we can look at that as an XY pair. We've walked 0 miles, and we're already at an elevation of 8,000 feet. We can plot that as an XY pair. Now notice, just to get up to 8,000, they did that little dash so they don't have to start at 1,000, 2,000, 3,000, just so we can jump and get right to the point. So that's a good move to make our graph look a little better. And then we realize, well, let's use this rate. If we understand the idea of rate, this idea of slope, again, I don't want to repeat everything that you've seen in algebra classes before, but the idea of slope, a lot of people also remember this old saying of rise over run. How far up, down you're going over how far left, right you're going. So if we apply that idea here, this would mean we're going up 650 feet as we go right 1 mile. So look how we did that. I go up 650 feet as I go right 1 mile. I would have a new data value. I started at x is 0, I went right 1 mile, hence the x is 1. I started at 8,000 feet, I went up an additional 650 feet, hence the y is 8,650. And now we could continue. We know this is a linear model, so we could just draw the straight line through those points, and notice what they keep emphasizing here. You go a mile of walking distance, you went up another vertical 150 feet. If you walk another mile, you went up another 650 feet, and so on. So, 2 ways to answer my question. Number 1 is we just made this model, and now we can look. Well, after walking 2 miles, that is telling me x is 2. We want to know what is the elevation. That's asking us what is the y. I'm sorry, let me get that back in the camera. Walking 2 miles, we've got x is 2. The question is asking for the elevation. We're asking for the y. So just because this is linear, we did problems like this from 9a. We go to our graph. There's the x is 2. Find the point on the graph. Go back to the y. But now here, we'd only ballpark it. We'd, okay, well, that's more than 9,000, less than 9,500. So maybe we'd say that's, I don't know, maybe we'll say that's about 9,100 feet. Maybe you might say it's about 9,200 feet. Again, sorry about that. I should point out I'm in the camera here. So now, looking, just roughly ballparking, and those were about my estimates. So maybe I just throw in between there, and I say it's about 9,150 feet. So a rough ballpark. So that's one of the limitations from a graph, that we do have to occasionally do those estimations. How can we get a better answer? We can practically apply what's happening here. Just think practically. Well, if I walk 2 miles, I mean, just what we're applying here. I went up 650 feet once, and then I went up 650 feet again. So I went up 650 feet twice, which if I add those together means I went up 1,300 feet. And if I went up 1,300 feet and I started at 8,000 feet, well, that would mean I finished at 9,300 feet. So you can see why ballparking, that's not a bad estimate, but I was actually off a little bit. And if you notice, I try to do this a little intentionally, everybody. Notice how when we try and draw left-right lines, how easy it is to just stagger a little bit. If I really did a better job, if I pull out a straight edge, so I've got an index card here, if I did a better job going left-right, I'm actually not down here, I'm actually more up here. So just how easy it is to sway a little bit, and now all of a sudden that makes a big difference. Here, I thought I was a little bit closer to the 9,000, hence That's why these were my guesses. But when I did a better job drawing over here, now it definitely makes sense that this is the accurate answer. Looking now, I see that's actually a little closer to 9,500, just a little bit closer. So that reinforces that this is the correct answer. So what I'm showing so far is just a little bit of practicality. We are applying the mathematical model. We're seeing how the graph attaches. But we're also seeing there is some room for just having some good experience, some good sense. And let's do that one more time. I walk 2 miles. Look at this rate, 650 feet per mile. I walked 2 miles. So one more little bit of work here. If I looked at 650 feet per mile and I multiply by 2 miles, we remember how our units work. That would give me 1,300 feet. But to realize, what are we looking at here? This rate was all talking about how much we went up, down as we walked. This tells me I went up a total of 1,300 feet. But what I'd have to do to finish this problem is to remember that I initially started 8,000 feet above the ground. So if the question just simply asked, how far up have we gone after walking 2 miles? We've gone up 1,300 feet. But since the question asked, what is the actual elevation? We had to go back and incorporate that we already were 8,000 feet above ground, and we went up another 1,300 feet, hence adding those together. And that's just what we saw here. Practically speaking here versus what we're doing here, and we're still confirming that same answer, 9,300 feet. I can understand if you're seeing a little bit of like, okay, we're saying a lot, but what questions should we be able to answer here? Just hold that thought, because as we get to the end of this lesson, we're going to point out one last way to look at these types of questions, and it involves making a formula and then relying on the formula. A couple you asked after class, we did something similar with this with expected test grades based on study time, and I'm going to come back and show you how to do that in this type of situation. So, first things first, we just looked at a nice linear situation, we saw a description, and we saw how, especially as they say, thinking of it as a linear function, that we were able to make that model and to be able to use that model or just think practically in terms of units to answer some basic questions. But now, as they move into example 2, they want to point out that, again, our lines don't always go up, that we don't always get positive slopes. So in example 2, they do this price demand function. They talk about pineapples, and they point out this trend that if you increase the price of pineapples, that the demand would decrease. So instead of getting one of those situations, our line is actually going this way. This represents a negative slope. So just looking at that actual slope formula, they already gave us 2 nice XY pairs. So if we applied that idea of rate of change, the change in Y over the change in X, look at what happens here, everybody. See, the easy thing that most people do that can easily make a mistake, they go, okay, Y minus Y, they go 80 minus 50, and then X minus X, and they go 5 minus 2. This is incorrect. You need to be consistent. What I just did here is the common mistake. I looked at the Y's, I looked at the X's, but I did that very natural thing people want to do. They did big minus small and then big minus small, but the big number here came here for Y, but the big number here for X was down here. Be consistent. If you use the 80 pineapples first in the Y, well, then you have to use the $2 down here for the X. So this would be positive 30 over negative 3. That would be negative 10. That would literally be negative 10 pineapples per dollar. And what that shows, the demand is decreasing by 10 pineapples every time you increase the price by $1. The alternative way to do this, if you started with 50 minus 80, well, you use this y values first. Now you would use this x minus this x. So now you get negative 30 on top divided by positive 3. Same thing. Positive divided by a negative or a negative divided by positive. The numbers are the same. We get 10, and both give us a negative as a result. So you could look at it either way. I've increased by 30 pineapples as I decrease by $3, or I decrease by 30 pineapples as I increase by $3, but either one gives me this same rate. But now let's take another look at this, and let's try and set up our own model similar to what the book did with this elevation problem. Let's make up our own problem, and let's look at a leaky bathtub. You have a leaky bathtub. You fill the tub, and it's a 50-gallon tub, so you put 50 gallons of water in your tub, and it leaks at a rate of 2 gallons per hour. I'm just going to jump in and ask a question, kind of like what we did with the elevation problem. I'm going to ask, how much water is still in the tub after 6 hours have passed? Okay, another situation. Let's think this through. Oh, and I want to put a constant rate here. This idea of constant rates, constant slope, that's the idea of what leads to the linear model. That's what we were saying here. Again, we keep doing that same 1 hour, 1 inch, 1 hour, 1 inch, or 1 hour, 1.5 inches, that we keep getting that same rate, and that's why we keep getting this perfect straight line. However far we go left, right, we do a distance up, down. And then we keep doing that same thing. I go the same left, right, I go the same up, down, and I keep getting points that line up on that perfect straight line. So how can we do this? Well, again, just thinking about our situation, we're looking at how much water is in the tub, and by this rate over how much time has passed, we're specifically looking at time measured in hours. So we got how much water in the tub, and that's measured in gallons, over how much time has passed, and that would be measured in hours. So just seeing that setup, I see that from my rate, 2 gallons per hour is establishing my situation here. What are some options? Well, some people, again, just thinking about the units. If I know 2 gallons per hour, and I know 6 hours have passed, if I multiply these, I see how all my units work out perfectly, and I'll get a total of 12 gallons. But to realize what we're actually doing, this is the rate we are losing water. This means we have lost 12 gallons. The question asks how much water is still in the tub. This is very similar to the elevation question. If I just said how far have we walked up the mountain, the answer was 1,350 feet. But when we asked the total elevation, we had to consider what elevation we started at. So same thing here. If I just said how much water has leaked out of the tub, we've lost 12 gallons. 12 gallons have leaked out. But since we know we started at 50 gallons and I lost 12, we would think about that. And the difference, understanding loss versus gain. In the mountain problem, we were going up the mountain, hence we added to our elevation. If we were going down the mountain, we would subtract that from our elevation. Same thing here. If I was pouring water into the bathtub, I would add this total to how much I had in the tub. But since we know this is leaking, I would subtract it. So that's why I really want to reiterate in this section, we've got all this mathematical modeling work, but there are a few different ways to think of these problems. And if you did a good job understanding the units and the problem solving from the previous problem, you could really do a lot of good work just thinking naturally through a problem, using those units, considering what that means, that this is not your final answer, and being able to incorporate that to get your final answer. But here's another option. Another option is to think about making the graph, just like they did with the elevation. To think about that we started with a full bathtub. So we'd start up here with 50 gallons of water in the tub. But now look at my rate. I'm going down 2 gallons for every 1 hour that has passed. So every 1 hour, I've got to go down 2 over 1, down 2 over 1, down 2 over 1. And that, do a little better here. There we go. That would be my model. Now we can realize that nothing happened here, so my graph should start right here. We can practically realize that at some point, the tub is going to be empty. There's not going to be negative water, so my graph ends here. But the important part is in this middle area. And then if I really think practically about 6 hours, I should have given myself a little more room here, everybody. I might be able to fit this in. That after 1 hour, I went down 2. 2 hours, I went down another 2. 3 hours, 4 hours, 5 hours, 6 hours. Let's pretend I've got a break here. So this is not 0. We're starting whatever this value is. But practically, I went down 2, down 2, down 2, down 2, down 2. Oh, and one more, down 2. So at the end, I kept going down 2. I went 6 total hours of travel. Keep going. Look at it. I went down 2, so I'm at 48. I went down 2. I'm at 46. Down 2, 44. Down another 2, 42. Down another 2, 40. And down 2 more, I reached 38. Again, I apologize. This is a poor graph. I should have given myself more room if that was my full intention to solve the problem this way. But just to realize that without knowing about y's and x's, just literally plotting points and applying the slope, we can really get a full picture. And if I did this really nicely on graph paper, just one time, go to the top at 50, I went down 2, so that's 48, as I went over 1. There would be 2 points. If I do a good job drawing that, I would be able to line up that when I get out to a time of 6 hours, that I would be at a Y of 38 gallons. So I could have just taken more time drawing this, and I could see, I could literally just do the XY, that I would know that this is asking me when X is 6, what is Y? And by doing a good job drawing the graph and drawing the straight line, I would be able to get that answer. Okay, so now moving along. Now the book introduces what they call the rate of change rule. And the rate of change rule, it's a little funny because when we take a look at it, we've already been doing it. And I keep reinforcing that. By understanding units, you can get away with so much more here because they're trying to give us this rule that if you know the rate of change and if you multiply by the change in the independent variable, so again, if we know the change in X, we can then find the change in the dependent, the change in Y. So if I do rate times, again, that's the change in X, then I will get the change in Y. So they point that out, going back and looking at one of the pineapple problems. But let's point out that we've already done this. We've done this twice already. That if we go back to my first question, what is the elevation after walking 2 miles? We knew, going back to our first example, we knew the rate was 650 feet per 1 mile. We're being asked, what is the elevation after 2 miles? Well, 2 miles, the 2 miles we walked, is the change in x. We started at the beginning of the trail, so after walking 2 miles, that represents that change. So we did the 650 feet per mile. We multiplied by the 2 miles, and we got 1,300 feet. But even going back when we did this, we kept pointing out that 1,300 feet was not the final elevation. It was how far up we have walked. How far up represents the change in y in this problem. So it wasn't the final answer. We just used the change in x combined with the rate to find the change in y, but then we used something about the original y to incorporate that change. So the original y was 8,000 feet. We went up, hence we added the 1,300 feet to know the total elevation was 9,300 feet. And then very, very similar with the leaky bathtub. We were told for the bathtub, the rate was leaking. So this is where it's good. We could just think practically with loss, but we could also incorporate a negative. That since the bathtub is leaking at 2 gallons per hour, we can make that a negative 2 gallons per hour. We wanted to know what was the amount of water in the tub after 6 hours had passed. So we started at time 0. We waited 6 hours. That represents the change in x, the change in the independent variable. We did 2 gallons per hour times the 6 hours to get 12 gallons. Actually, and again, even better, at that time, we just thought practically to realize that, no, we're losing water. We lost 12 gallons, but that's what the negative can do. If we thought of this as a negative 2, then this would be a negative 12, and that negative should be understood as some sense of loss. Hence, at the very end, we knew we took the original 50 gallons and subtracted the 12 to know we had 38 total gallons of water. So this is a nice formula. And there's a couple of homework problems that talk about use the rate of change rule. I mean, the test you'll get on this is going to be a take-home. So if you prefer to think of it this way, that's fine. To know, okay, rate of change rule, this is what it says. But to realize, again, good understanding of units, you can do this work. But just to realize, just because you get this, this has the correct units. But to make sure, does that actually answer the question? No, it did not. This had the right units as well. But to realize, again, we had that one extra component to get that final answer. All right, so now we can get to the punchline, the finishing touch. So these linear functions do have a general equation. So we did say this in class. We mentioned the reminder that for a lot of people, these equations, they remember the old algebra, y equals mx plus b. M is your slope, b is what we call the y-intercept, the y-coordinate of the y-intercept. So that's the old algebra formula, but they give us a whole bunch more. They actually give us this nice little example to think about, but eventually we get similar to what we just did with that rate of change formula. We get a general formula, but instead of y and m and x, just to think about it, the dependent variable, y, is always equal to some initial value that corresponds to the b. That's the only tiny difference. This formula, it's like writing b plus mx, but in algebra, we often flip those the other way. But that initial value is the same as that b plus the rate of change times the independent variable. There is your m times x. So if we have that, or if we can find that, let's go backwards one more time. Actually, let's do it for both of them. If we look at the elevation, we were told our initial elevation was 8,000 feet and that we were climbing at a rate of change of 650 feet per mile. So now we can go back and I could find the equation of this. And I could say, okay, this straight line would have an equation, y equals y, the dependent variable, my initial value of 8,000 feet. A lot of people at this stage, you can use the units. Actually, I'll put them in right now. Feet plus my rate of change, 650 feet per mile, times x. If we have that whole equation, now you go back to that problem one more time. What is the elevation after walking 2 miles? No more rate of change. No, we could just plug it in. That question is, go back to it, x is 2, what is y? Well, now if we plug in x is 2, right over here, technically it would be 2 miles. And that's where for a lot of people, if you're going to do this, a lot of people don't like the units while you also have variables. It just can easily lead to little goofs and mistakes. So I get 8,000 plus 650 times 2. Do the arithmetic, and you'll get that same 9,300. And just remember to include the units feet. Okay, let's go back and let's do that same thing with the leaky bathtub. With the information we were given, we can do that same thing. My leaky bathtub leaks at, at a constant rate of 2 gallons per hour, and we initially filled the tub with 50 gallons. Y equals the initial 50 gallons plus a negative 2 times x. Now, some people remember that plus a minus, you could just make that 50 minus 2x. But others prefer it. The formula says initial value plus rate times the independent variable. So they always like to have that plus, even if this is a minus. But now, same thing. We know if x is 6 hours, well, now I could just plug in x is 6. 50 minus 2 times 6, that becomes 50 minus 12. So we get y equals 38. But of course, include our units. Y equals 38 gallons. All right. So last, very, very last idea. And this is the big part. The idea of rate of change, whether we're looking at the graph of a linear model already given, to be able to use it, to be able to find slope, rate of change, to be able to discuss the rate of change in terms of words, to be able to use a rate of change to answer some basic questions. So that's what we've seen so far. The last little bit is that we can actually find the equation just from having 2 data points. What we've been doing in these last couple, what I did right here, I follow the formula knowing the initial value and knowing the rate. But let's just do one very, very last problem that just uses 2 data values. They've given us a nice little step procedure, and basically what it is, it starts with use the 2 points to find the slope. We've done that before, but now let's just extend that process. They talk about being able to use any XY pair to then move on, but I'm going to be a little more specific for us. So we are going to look at a bucket has 4 inches of water in it. It starts to rain. And after 3 hours have passed, the bucket now has 10 inches of rain in it. assuming it rained at a constant rate, let's find the equation of this model. If we wanted to just draw the graph, we can think about things and say, okay, what do we have here? The bucket already had 4 inches of rain, 4 inches of water before it even started to rain. So if I think about my time, and since we're seeing other mentions of hours, we'll continue to use hours as my units. And we're talking about how much water in the bucket. And we're measuring that in inches. Well, with this setup, before it even started to rain, we already had 4 inches in the bucket. We could think of that as an XY pair 0, 4. And then next, we look here, well, after 3 hours of rain, we've got 10 inches of water in the bucket, 10 inches of water. So that would be an XY pair 3, 10. 1, 2, 3, 5, 6, 7, 8, 9, 10. That point would be up here, and we could think about that being my linear model. So, I could go backwards now and ask about how much water is in the bucket after 1 hour and so on. But our question is finding the equation. So it's nice that we drew this picture. One reason I did want to show you that was just to be clear, right? We could see that we've got a nice positive slope here. But the big picture is, how am I going to get this equation, whether I think of it as y equals mx plus b or y equals initial value plus rate times x. I've got an initial value. When time is 0, that's what we mean by initial value. Whatever we're measuring, as soon as we start the clock, before we start walking the trail, before it started to rain, right? That is my initial value. And that's the one technical aspect of b. It's just the y coordinate of that initial value. So I get y equals 4 plus the rate times x. But what is my rate? That's where I'll use my slope formula. I'll look at the rate is y minus y, so I get 10 minus 4, over x minus x, 3 minus 0. So I'll get 6 over 3, which equals 2. And specifically, that would be 2 inches per hour. So if they just ask us for the rate, we could figure that out as well, having those 2 points and being able to find the rates of change in each component. But to finish this question, we've got y equals 4 plus 2 times x. So now that we've got that equation, we can do things like, let's just answer 2 quick questions. How much water in the bucket after, let's go 2 hours. That would be my x value. And we can go through the whole thing that we used to. It's not a problem to think about, okay, well, there's my change in x. That times my rate would give me my change in y. We'd end up that the water has gone up. Actually, no, there's too many coincidences here. Let's make this after 1 hour. So after 1 hour, I've got a change of 2 inches in the water height. Well, since it initially started at 4 inches and I went up another 2 inches, I would know that I've got a total of 6 inches of water. So all those same things we've been doing, there's nothing bad about that. But just to point out with the equation, we can just do a nice plug-in and it takes care of all that for us. We got 1 was the amount of time, so x was 1. Y equals 4 plus 2 times 1. 2 times 1 is 2. 4 plus 2 is 6. We've got a matching 6 inches. But what's especially nice here, especially with estimations, right? That's always the trouble with the graph. Trying to look, trying to ballpark. Did I do a good job with my graph? Not bad, right? If I look at this, there's 1 hour. I look like I'm lining up with 6, and that does, I'm sorry, 1 hour, and that does look like it's lining up with 6, and we're seeing that confirmed right here. So if we had a trouble doing estimations up here, or like you notice, I did this very quickly by hand, there's a good chance that there's a little bit of mess. It's tough for me to be perfectly consistent with all my dash marks. So that's a more reliable way to not just estimate, but get a good final answer. But now let's see how we can reverse this. How long will it take for the bucket to have 9 inches of rain, 9 inches of water? So again, ballparking, if I go to the graph, now I've reversed it. Here, I gave you the X, we went to the point and did our best to find the Y. Now I've reversed it. I'm asking you how long, I'm asking for X, and we know this is Y. So I could do my best for my graph and say, okay, well, there's 9. This point is taking me down here. So I'm more than 2 hours, less than 3 hours. Is that 2.5? Is it 2.6? Is it 2.7? It's a rough estimate, but by using the equation, I could plug in 9 for Y. Just solve for X. I would get 5 equals 2x, divide by 2. 5 over 2 is 2.5 equals x. That would be 2.5 hours. Which that was roughly what I was suggesting. But again, it wasn't perfect. Could I tell that was exactly 2.5? I don't know. Maybe that would have been my guess, but I might have guessed something like 2.6 here. But now I can see from the equation, it's exactly 2.5. So that's it, everybody. On Monday, again, we'll do a couple of these problems just to review and remind you. Test 3 is going to have several problems like this, several problems like we saw on Monday. So should be a nice take-home test. And again, Monday's class, we'll still have lab 4, very quick lab at the end of class. And I'll remind you a few details as far as the final exam to make sure you're studying and on the right track. And of course, 9B, the last homework assignment, make sure you're finishing your homework component to make sure you get a good grade. Okay, everybody, that's it. I'll see you on Monday.